and Vlad and everybody else who bring all these friends together and give me the opportunity to actually reconnect to some of the quote-unquote friends that I never know. It turns out today I found out that many of the speakers here were actually associated with Richard Skeletar on the DQMC stuff. And perhaps it comes with a surprise, even for Vlad and some of the close friends. Actually, I was a postdoc of Skeletar. I never actually pursued this DQMC as my career, but I was actually working with him for more than 2 years. So it's really good to see all these friends, and also give me a chance to share some of the actually a tiny baby project I stumbled into. I was going to talk about some more complicated correlated physics about high DC, but then I realized that a lot of people here are interested in frustration, and it turns out I have stumbled into this small project I find quite interesting and might have some implication in the long term. So I decided I'm going to talk about this for the first time. I've never give a talk about this subject. So please forgive me, I'm still missing tons of references. And also, on top of that, please forgive me, I haven't changed my clothes for like 3 days because my luggage is still somewhere between Paris and here. So I have the perfect excuse not to dress up formally. Of course, I never do, but nonetheless, now it's good to have a good excuse. Okay, so let me proceed by, it's a little bit hard to see. So the topic of this talk is about localization in a homogeneous system due to geometric frustration. All right, so I actually, to be honest, I'm never a big player in this field of localization, and of course, Vlad and many of collaborators are much more of a real expert. But I just stumbled into this project, and that forced me to think about what localization really means. And after sitting down and talking to some of my friends, especially my undergraduate student, I realized that it's actually non-trivial, because localization really means that we have to defeat the kinetic energy. It is the kinetic energy that moves things around. So you have to somehow defeat it. And that means localization is something very non-trivial, because in essence, the kinetic energy is the reason why we really have all the non-trivial physics in quantum mechanics, right? Coherence and everything else were designed to keep track of kinetic energy. So imagine that we can defeat it with a strong trapping potential. So this looks like a pretty standard thing to do, right? If you want to defeat the kinetic energy, you trap it. You trap it with a strong potential that at some point you could, in principle, trap the wave packet such that the tail is exponentially small. So this sounds like a perfect thing to do, but unfortunately this is not quite enough, because in a solid, we have all these atoms very close by, so this tail may overlap when they are not quite at an exponentially small regime. So the concept of localization in a solid is much more subtle, because of the fact that once you have uncertainty principle, a quantum object still can tunnel. And that makes this localization intrinsically a quantum problem. So how do we trap a quantum object? Well, you can try to suppress the kinetic energy below the scale of some other physics. For example, you can try to go to very high temperature such that kinetic energy becomes more or less irrelevant. You can maybe introduce intraatomic repulsion like Hubble U, then that will give you a chance to get to the mud insulators. You can also switch on electron lattice coupling that could, in principle, self-trap a polaron or other type of boson as well, if you couple to other type of boson. And finally, we can also think about if you now have a short-range binding, then in a lattice, this will also lead to great suppression of kinetic energy and maybe even phase separation. So this is the most physical thing to do, because you have some competitor that suppress the kinetic energy. So once this happens, the kinetic energy becomes a small perturbation, and then whatever physics is supposed to be introduced will be suppressed and maybe even become completely irrelevant. Now, another approach, which is much more subtle and actually very subtle, is that you can try to damage the kinetic energy itself. And this is where Anderson's idea becomes really shine, right? By using disorder or something else, that you can damage the coherence or the kinetic energy to the point that you can actually localize or weakly localize the state that could be very large, but still localized nonetheless. And what I have not paid attention to until recently was that, in fact, geometrical frustration also can damage the kinetic energy, but now in a homogeneous system. And this is, of course, quite interesting in the sense that you have a transition of symmetry, which you would think naturally promote momentum being a good quantum number. But with geometrical frustration, you could, on the other hand, completely disable such physics such that they don't move, okay? And there are a lot of concepts that was foreign to me, but with this little project I'm going to show you, it turns out that this really forced me to rethink the basic quantum mechanics from the beginning. After this project, I think I'm ready to write a small chapter about the beginning of quantum mechanics in a very different way now, with a very different perspective. Now, so why is the localization such a fascinating phenomena? Well, obviously, for transport property, this localization will have a dramatic impact, right, on transport. Of course, we like transport, but not necessarily best transport. In many cases, like thermoelectric or thermal conductivity, we actually may want things that are not so good at metal, right? So nonetheless, this kind of localization really matter a lot for physical behavior, particularly for transport. But modern days, there are a lot of people who are thinking about information. And then the localization becomes even more interesting because once you have localized state, they don't move. So there is a very limited way for them to conduct the transfer of the information through coherence, right? So as a result, you can detect very strange entanglement entropies and so on. And this localized state could be used to host some information, some quantum information that can live long enough. And you can use it, supposedly, for quantum computation or storage. And associated with this localization is also that once you have a localized state, assuming that you have many of them, then, of course, the system will have a hard time to thermalize because the information doesn't flow, the entropy doesn't flow, nothing flow, then, you have a system that can wait long time, you can wait for a long time and you never reach thermal equilibrium. And these are the kind of things that, like, people talk about the ETH, right, the ergodicity, some hypotheses that doesn't quite work and so on. I think there are a lot of things in quantum mechanics that we have been taken for granted, and localization actually is the key to unlock many of these interesting behavior. So even though I'm not really in this field, once I do this project, I develop a full appreciation of the localization. Not necessarily about a disorder per se, but localization itself in quantum mechanics. Now, I mentioned two possibilities. One is to use something else to compete. The other is to just directly destroy or damage the kinetic energy itself. Now, of course, you can think about combining them. Let's say you take an Anderson localization system and you switch on some many-body interaction. Then, of course, you can ask, how is that new interaction going to modify the localization? And that's where people are studying this many-body localization and many interesting behavior there as well. But to me, what's really interesting is that I dig up some literature and find a lot of contradictory claim about geometrical frustration when you switch on interaction. Okay? For example, I noticed that in the Bose system, when you have a fully frustrated system, you have a flat band. Then typically, when you have a flat band, you have an enormous amount of degeneracy. Right? Entropy is very large, and intuitively, you would think that once you switch on some interaction, everything coupled to everything in quantum mechanics, then level repulsion principle come in, you're going to lift the degeneracy, and perhaps break this a flat band into some finite dispersion and develop some kind of coherence, right? And that's what this paper is about. It shows that you can actually develop superfluidity by switch-on interaction. And then recently, based on that, people start to talk about, in such a similar system, quantum geometries and all these quantum matrix as well, right? So this is a topic that is still very much alive. But nonetheless, there is a lot of question about whether this idea is correct. And so I think, to me, this generation of effective kinetic energy in these cases are very interesting, but at the same time very puzzling to me. And after thinking about it, I start to have some question about this. So here are the questions of this talk. how robust is the geometric frustration-induced localization? Particularly, can local density-density interaction defeat such localization? Okay, that's basically the question. All right. Now, so let me start with a simple exercise I did with my postdoc and with my student. That was after some long struggle, we finally figured out the answer and analytically and published in PNAS last year. So here's the well-defined long-standing problem of boson. In near the quantum critical region, when you have a superfluid to insulating transition, near the quantum critical point, people observe the resistivity go through a finite resistivity change. And you can actually, I think even Bose group even show that this such a superfluid to insulating transition involve a quantum resistance, which is basically telling you the carrier is charged to E boson. But this is very surprising because, as we all know, boson is they like coherence, they do condense. So they most likely have superfluid phase. So they don't have resistivity at zero temperature limit. They cannot. They become superflow, right? Unless you manage to use a very strong interaction and drive them into a insulating phase. Then the resistivity goes to infinity. So for boson, it's one way or the other, right? There is no middle ground. Either resistivity is infinite or it's zero. There is no middle ground. But all this experiment is indicating that you can have bosonic carrier with finite resistivity. This is the infamous question, so-called quantum Bose metal, right? Zero temperature limit metallic behavior with finite resistivity. This is a long-standing problem that many people have tried, many ideas, including one of my close friend, Philip Phillips. They tried very hard to understand this, and in this review article he wrote, he basically concluded that all the ideas so far are very unstable. Okay? So we were not actually looking at this problem per se. We were looking at a general idea, which unfortunately I won't have time to talk about, that can one understand this non-conventional superconductivity from a very different perspective. Namely, if you have some kind of high energy physics that drive the system to form a tightly bound boson. Two fermions bound together like hydrogen bind into a hydrogen molecule in ambient pressure, right? Now, if you look at the ideal gas we have in this room, they are H2. There is no H1. You can ask why, but that's not important. For my energy scale, they are H2. I treat them as ideal gas. Good, right? So what if something like that happened? Then you will see that some of the spectral wave of the fermion will be stolen into some well-defined localized object like the bound boson, which is actually, of course, has its own kinetic energy, but different from the fermion. Now, in some regime, when the binding is strong enough, but not too strong to drive the system into a BEC limit, you actually have a situation when the boson dominates most of the physics. And there's a tiny amount of fermion that survive. They don't matter for the physics unless you explicitly want to look at them. Okay? So this is, of course, something that a lot of us, including myself, will be very uncomfortable because all we know about textbook is one particle Green's function fermion tell you 99.9% of the physics. But here, in this situation, the boson control the physics. The residual fermion, if you want, you can think about them as a probe to the boson. They don't matter. But if you see them, you can see the boson through them. Okay? And this is a very interesting possibility because that explains why we've been seeing those Fermi surface and all this phenomenology for 20, 30 years. We still couldn't explain unconventional superconductivity. Perhaps we are looking at the wrong object. Imagine you have a probe to probe the H1 in the air. But really, the quasi-particle is H2. Imagine what you will see. You will see a mess. Because H1 in the H2 will move in some weird way. And they don't look like a quasi-particle at all. They have a continuum spectrum. It's a mess. You're not going to learn much because they don't matter, right? So this is a possibility we were exploring, but unfortunately, I don't have time to talk about this. I just want to show briefly that this particular idea we have now one Hamiltonian, one set of parameters that I fixed more than 10 years ago, and over the last 10 years, I've been working with a bunch of undergraduate students and junior graduate students to try to investigate on many different physical properties that one can study for this particular model. And we found that we can explain many non-thermodynamic behavior in almost trivially, right? Of course, you can actually argue that, well, I don't like this starting point. Yeah, me neither. I never actually liked this idea. But nonetheless, it worked. So after a while, my students say, well, no, we have to take it seriously. Because every time we try something, it worked, right? So we keep working, and now we have more in the list. I can show in private to you. Almost everything non-thermal liquid that you have encountered is beautifully reproduced by this model. One Hamiltonian, one set of parameter, never readjusted for more than 10 years, okay? But today, it's not about that. Today is to say, well, in this investigation, we stumble into a problem. So this is everything we have done so far, and they all beautifully explain many of the behavior, not just a Q-plate, in general. All the non-thermal liquid behavior is trivially explained. But what I'm going to tell you today is that there is a region, an underdome region, that you can go to 0 temperature and you never have superflow. Now, for a bosonic system like this, it will be a problem, right? Because boson always condense. How do you have no condensation and no superfluidity here? So that problem is what I'm going to tell you today. And well, this is the model. It has a very simple idea that you take a fermion system that you like, you bind the neighboring side into a boson. That's it. You can take any lattice you like, bind them into a boson. So the boson will live on the bound lattice. So you change the lattice from the fermion to boson, and you will have different symmetries and everything. And this turned out to be very interesting and important. Nonetheless, for this kind of model, we found in one of the earlier studies that it actually has a D-wave superfluidity at low temperature. And then, if you now go to a smaller doping, what you find is that there is a mass enhancement around 5%, such that the D-wave superfluid will have no stiffness. So you cannot have a superflow. But what's interesting is below that 5%, we have a very weird situation where you have this flat line degeneracy in the band structure. Line degeneracy implies geometrical frustration. So we look into this a little bit further, and it turns out that indeed, this flat line, which is, it doesn't matter what kind of parameter you put, it's always there. It could be here, could be here, could be somewhere, but it's always present because there is a hidden geometrical frustration in this lattice. For example, imagine you have a wave function like this, plus, minus, plus, minus. And then you want to connect with another lattice here, right? You find that this guy can want to hop here, and this guy want to hop here. But their hopping are identical. So they will completely frustrate their phase. As a result, they don't move. This is called perfect interference, right? This is always there, and that's why there is a flat band. And when this becomes the ground state, you have a situation when the boson doesn't know where to condense. So as a result, you can show that this is very well protected by actually a symmetry operation, so-called local point group symmetry. And the number of this symmetry is the system size. And that's why this is very robust and not easily broken. In this recent paper we published, we were able to show rigorously, analytically, that this localization, this is a one-dimensional localization, right? It's a 2D quantum state in a 3D world because it doesn't move in the third dimension. We can show that this protection, the geometrical frustration protection, survive interaction, density-like interaction, okay? And how does that work? It's actually not very difficult, so I'm going to spend easily 5 minutes to explain how this works. So first of all, you look at this particular state and look at the kinetic energy only. You can see kinetic energy is the only one that moves the object, right? Interaction doesn't move them. You just take them out, take a look, and put them back. It doesn't move. Only kinetic energy moves them. But this particular state happens to be an eigenstate of the kinetic energy. As a result, it doesn't move. Once you have this state, you apply the Hamiltonian to it without just kinetic energy part, it survives, it stays, it doesn't move. It doesn't go to the next object, okay? And for the same reason, if you now calculate the current operator, you'll find that it just gets back to itself. Right? It doesn't go anywhere else other than stay in the plane. So clearly, this many-body Hamiltonian is telling us that the kinetic energy part or the current part will not allow this state to move. And therefore, intuitively, you will think that, well, this state will survive, even if you have a many-body interaction. But to really improve this to most experts, you can think about this probably an easier way. Let's think about the one-particle Green's function, which gives you the band structure. You want to add the particle somewhere in time and then propagate after some time and remove it, right? That's the definition of one-particle Green's function. And you can show that, well, this Green's function is a superposition of many Green's functions together because you can start from here and move, or start from here and move, and everywhere else. But the problem is that when you start from here and move, and you start from here to move, you need to add them together to form the correct superposition that gives you this state. So what you can see very easily is that if you start from somewhere in this state and try to move out, you will get a one-particle Green's function that can move out. But when you combine them with the proper superposition, they always cancel. This is called symmetry protection. So you can easily show that within path integral formulation, such state, this single particle state, would never move even in the many-body system. Okay, that's what we have found here. So you can also go more detailed and more carefully and show that, oh, what if I happen to have hit another particle? So the many-body interaction will be in action here. And then things will be different. But then again, the symmetry will dictate that whatever you do, there is an equal probability that you add a particle in the other side, and then there happen to be another particle there as well. So you can show very easily the moment you move out of the system, these two contributions exactly has a minus sign, and they will always cancel. In other words, the one-particle Green's function is always 0 if you try to take a state like this and move out of the plane. Okay, this you can show. Now, this is a simple one-particle Green's function. But it turns out this goes even deeper. You can now think about, what if I have a real many-body system? Do I have a superfluidity? I don't want to measure with the current correlation function, with this non-interacting particle I add, and then some other particle I move, or some current correlation. Well, I want to look at a many-body wave function. Can I show there is a many-body localization, right? Well, to do that, it turns out you can do it analytically as well, because there's this idea of canonical transformation that people are familiar with, but not so much in the second quantized form. So this turned out to be a great tool for localization study. So let's say you take a Hamiltonian. You know there exists a unitary transformation in the many-body Hilbert space such that this Hamiltonian will be brought into a diagonal form. They exist, right? And that unitary transformation that changes A to B will, of course, convert this B into many one-particle, two-particle, three-particle fluctuation and so on. It will be a many-body rotation. But nonetheless, once you bring them into this canonical form, this diagonal form, you know the many-body eigenstate is simply a direct product of all these bosons that you can add into a vacuum. So this is a very beautiful and simple thing to do. You have a simple direct product, meaning that you can take a particle from here and move it to another state. Oh, that's another eigenstate. You can then take one of these bosons, move to another state. Okay, that's another eigenstate. You get access to all the many-body eigenstates with a simple direct product. That sounds too good to be true, right? But it's not, because every one of these one single particle object comes with a many-body wave function, with the kinetic energy dominant one-body term, and the interacting induced density fluctuation all show up as part of the many-body wave function. Now, this representation turned out to be great when you want to study many-body localization, because once you have this, you can easily make the argument that because the unitary transformation that diagonalizes the Hamiltonian must respect the symmetry. Therefore, if you have a parity, like what I show here, if you have a parity, like here, that this guy along this point is R parity for this mirror image, while everything on this line is even parity, you can easily show that this fully dressed many-body, one-body object actually also had to respect the symmetry. So if the single particle wave function is odd, then the many-body wave function of that one-body object, the single particle, is also odd. And for that reason, anything that you start with this R parity stop to jump to an even parity will always be 0. So that means what? That means you can now dump the system, the particle into the system, into those many-body wave function. You populate them, and then they will not move. If you put them in those states, they simply won't move. And this is a very easy way to write a many-body localized wave function. And you can see immediately that none of these particles will move if all you do is dump them into this state. Okay, so that means we now have a true many-body localization. And now what happened to the transport? Well, obviously, if the particle can only move along themselves and can never turn, you will never be able to measure any meaningful transport, not to mention superfluidity. So this system, we can prove that this is a system with 0 superfluid density at 0 temperature limit. But it has no gap. It's not an insulator. So it will have a transport, but the transport is no longer protected by the coherence of the system. So you will have a dissipation, and therefore it is a quantum Bose metal. So we proved that this is a quantum Bose metal, and it turns out this is the first one I found, as to my knowledge, that is uniform. The system is no disorder, and still is not able to establish the full coherence. And the reason is beautiful, because frustration, geometrical frustration. So with this in mind, we come across an interesting measurement by Geom and Bose. They show this transverse measurement that there's something funny about the transport. If you look at the Fermi surface, the largest Fermi velocity happened at the 45 degree. You expect the transport, the resistivity, to be lowest in this direction. But it turns out it's the opposite. It's smaller in this direction. But that's exactly what we have in this paper, because you see, the low energy state are actually, they like to go vertically or horizontally. So naturally, this very nicely agree with what I see. But with this in mind, then you can ask, well, this geometrical frustration is very subtle. If I put impurity, I can break it locally, right? But more importantly, what if I apply a unit axial pressure? I can lift the degeneracy. I can break the perfect geometrical frustration and allow some coherence, right? Well, when that happens, these guys will start moving. They will start propagating, and then they will have superfluidity. But this particular state is actually D wave in the plane. So as a result, there's a prediction of this theory. If you now apply uniaxial pressure to this Q-plate, for example, you will find a very low temperature, unfortunately, depends on the pressure you apply, that you will see a P-wave superfluidity. So you will see another dome of superconducting behavior, just very low temperature. But because the symmetry is different and there is a mass divergence in between, there is always going to be a quantum critical point. So there is no way you will miss it. It will not be like a tail of the original dome. No, they will be two separate domes, separated by a quantum critical point. So this is the prediction that, unfortunately, very much depends on how much you can put the pressure to break the geometrical frustration. So it wouldn't be a very high temperature phenomena. But nonetheless, if this can be shown or can be found experimentally, it's a smoking gun. It's telling you the entire phase diagram is bosonic. Okay? All right. So that was the story. And now, before I finish, I want to quickly tell you what are the implications of this. Other than all this information, symbolization, all these people were interested. I'm interested in transport. I'm interested in physical behavior. So you can ask, now if I have this Bose metal, and then now I couple to this residual fermion, that doesn't matter, right? But now I can couple those fermions to them, and then I can measure those fermions. So I'm probing the probe of the boson. So these fermions I'm probing themselves serve as a probe to see the boson directly, okay? So what would happen? Well, as we show, you can do that, and this fermionic carrier behave like a probe to the emerging Bose liquid here. Right? They help you see the boson behavior. So if you do that, then you realize this EBL mean field is weird, because this state has incomplete coherence, right? Because it cannot move across the plane. There's no way to establish coherence. So even at the 0 temperature limit, this mean field has no coherence. It has coherence, of course, in certain dimension, but in certain other dimension, they lack coherence. So this is, to me, to my knowledge, the first mean field I have ever encountered in my life that has some residual phase freedom. And now, with this coherent and partial incoherence, in the system, you find something extremely interesting. You can couple to a free fermion to them, and what you see is that near the nodal area, you develop a non-Fermi liquid scattering rate. Namely, you go down to the temperature, low frequency limit, fermions still have a finite scattering rate. It never disappears because the number of bosons is fixed. So you always scatter against those incoherent bosons. As a result, there is no Fermi liquid behavior whatsoever. That's number one. Number two, you also find that if you now move on to the antinodal region, then you find that the scattering is stronger. As a result, you open a pseudo gap. So that means altogether, scattering such a Bose metal mean field will give you a dichotomy of nodal antinodal region and develop, well, maybe I can tell you why. Well, if you look carefully here, the nodal region, you scatter against all the fermions on this line, and they are very different in energy, so the scattering effect is not too strong. But if you're near the antinodal region, then you're scattering against many states that have similar energy. So the effectiveness of scattering becomes stronger. So simply because of that, you generate the dichotomy and you generate the Fermi arc. Okay? Now, this pseudo gap has a very interesting behavior that at the point when you cross the Fermi energy, so there's a Fermi wave vector, when you open the gap, typically you expect that's where you have the minimum of the energy when you open the gap. But in this case, because you don't do a 2x2 matrix scattering, you scatter by a bunch of momentum, it turns out the minimum of the energy is offset. It's not at KF. And it turns out this is exactly what artists have seen all along, that when they open a pseudo gap from high temperature to low temperature, the minimum of the gap is not at KF, it's offset. And it's exactly what we see here. Not only that, now you can also ask, what if I made this Bose mean field weaker by raising the temperature? Well, you can see here, by hand, I reduce the density of that mean field. And then what you find is that you don't close the gap, the pseudo gap. Instead, you fill it out with more and more state. So by the time you get to half of the density, you already filled out the gap. So this pseudo gap temperature that people talk about in this picture is not a phase transition. There is a real phase transition at high temperature. But before you get there, you already filled out the pseudo gap. Okay? But there is a real phase transition because you start with a stiffness in the other direction, and that stiffness eventually will disappear. So there will be some kind of BKT-like transition at higher temperature. But we haven't seen that because before that, you already lose the pseudo gap. Okay? Now, so this pseudo gap also has a beautiful property that if you look at the momentum, okay, if you look at the momentum, you'll find that for a particular momentum, it's not symmetric. Oh, I'm missing a slide. Okay, so I'll just tell you, you see that this gap edge is not symmetric in energy. This is what Peter Johnson and many people have found. For each momentum, they are not symmetric. While in STM, you look at the energy of the gap, they are always symmetric. And it turns out, our calculations share the same phenomena. And I can explain to you in detail why, but I don't want to maybe spend too much time distracting you. So finally, I'm about to end. I want to tell you something work in process that is basically identical to what we have, but just 1 minute. Now, imagine you take not that particular system, but a system with a full frustration. Now you have not only a line degeneracy, you have an entire plane of degeneracy. The question is, would that degeneracy be lifted as people have claimed to have superflow? Well, I don't know the answer completely, but following a similar argument that we have proven, it seems that analytically, we convince ourselves that the answer is no. Density-density interaction cannot lift this degeneracy. Now, there's some subtlety. I'm not 100% sure about the orthogonality. There's a little bit subtlety, and so we're still checking numerically. But nonetheless, the current conclusion, which hopefully won't change, is that no, it won't be lifted. So at the end, your conclusion will be, this is my conclusion, that the one-body Green's function for such system will still be flat. The flat band cannot be lifted by interaction. And there is no phase difference possible for superfluidity. U1 symmetry cannot be broken unless you first break the geometrical frustration through, for example, spatial symmetry breaking. Many-body localization is realized, and it's similar in many ways to the many-body scar that people are talking about, but a lot simpler. Finally, it has many implications in the long term for transport entanglement and thermalization. Finally, let me acknowledge my postdoc student who made all this possible. So thank you very much for the attention.
Thank you very much. The talk is now open for discussion. I see people seem to be pretty tired. Oh, there's a question. Okay, go ahead.
Hi, I have a question about the pseudo-gap regime, right? Because what is the main message to use this kind of boson system? Because if you look, for example, Larry gamma A, they're able to show the pseudo-gap regime, and they're able to show the nodal-antinodal dichotomy. Why do we need this model exactly? I didn't understand.
Okay,
the whole problem.
The answer to that question lies in the real question for all the experimental and presumably theoretical researcher. That is, are we only satisfied by one theory explaining non-fermionic scattering rate, one theory explaining bad metal, another theory explaining strange metal, another theory explain the coefficient, or are we after a real understanding where I can use one picture to explain everything? Right, that's the question. And we have this model, which is very simple. Everybody is welcome to try. And in this model, we were able to explain all this non-trivial physics with same Hamiltonian. Now, obviously, each one of these behavior can be explained by many, many theories. But how many of them can also explain the rest? So the answer to your question is yes, for individual property, all these ideas probably are all legal and valid and very valuable. But do they describe the reality? Do they really describe this particular set of material? We don't know. And how do we know? Well, if you have a theory that gives you all these check marks, well, you probably should take it seriously. It may not be the only one, but it's a work in progress. Better than other work in progress. Do I answer your question?
I do not see any more questions. Oh, okay, sorry about that.
Just have a quick question about your last part, which I understand was on Kagome and frustration and what happens if you include many-body effects on top of that. So I'm not sure whether I got the interpretation of your result correctly. So one question you could ask is, suppose you start with, let's say, a Hubbard model.
Mm-hmm.
If you start with a tight binding model and a Kagome lattice,
Mm-hmm.
Then you have a flat band.
Right.
Now, was your conclusion that this flat band will not be lifted by interactions?
It will not be lifted by density type interaction, particularly local U will not lift that degeneracy. That's the conclusion. At least that's the conclusion we have so far. We are checking this numerically as well.
Okay, so I mean, on general grounds, you might expect that their longer range hopping terms will be generated in principle. And
exactly.
The longer range hopping terms will of course lift the flatness of the band.
That's what you expect. But according to our analysis, if it's density type, probably not. We'll check. We're checking this numerically. But the point, this is a little bit surprising. Because we are used to do some in-field decoupling, and usually you generate stiffness. But the point of this proof is based on rigorous mathematical analysis on the symmetry. And when there is enough symmetry, how many system size symmetry? Every point has a local point group symmetry. And they protect some part of this protection. There's enormous amount of symmetry that protect this flatness. It cannot be lifted by simply adding some simple density-density interaction. That's the surprising part. Once we can verify this numerically, we'll publish it. Then I think this is important to remember.
Yeah. Okay, thanks.
Thanks for your talk. I have a rather fundamental question. So Are these bosons virtual,
No, this is real boson.
What's the microscopic origin of those of this entity?
Right. Actually, many of these results that people think might be similar to the boson that we are used to, right? Phonon, megnon, whatever, orbiton, whatever. But they are not the same because at low enough temperature, those excitations all disappear. So the bosonic density is not a fixed number, they all disappear, right? But this is what Watercon called the type 1 boson. This is the real bound state of two real electrons or holes. So their number actually saturate at low temperature, which you can say almost become the doping divided by 2, if you want, right? Roughly speaking. And as a result, they survive at a very low temperature. And if they don't have a coherence, whatever fermion scatter them, they will no longer have a full coherence that you always expect from a fermionic system. But not in this case. That's why you can get non-fermi liquid scattering rate even at 0 temperature limit. These are real bosons that somehow have a hard time becoming coherent because of geometrical frustration.
So I think I can ask this final question. So you basically are saying that there are preformed pairs, right?
Yes, you can say it's preformed pair.
Preformed pairs. Now,
I would call it a molecule of electron.
Fine. That's what preformed pairs mean, I suppose, right? So now
No. Be careful. Preformed pair means many different things. Depends on who you talk to.
Well, okay,
right?
but there are strongly bound pairs like helium-4.
Right.
Now, presumably there's physics measured at very high temperatures, which was identified as strange, like linear resistivity going to 1,000 Kelvin. Now,
right.
So basically, the discussion whether your thinking and someone else's is the same or different or orthogonal or is this even possible has to do with the question, can these bound states or preformed bosons as such entities exist up to 1,000 Kelvin? Now, my question to you is there an experimental way to determine whether they are preformed pairs, in other words, superconducting fluctuations or not?
Right.
Can you experimentally answer the question?
Okay.
People have tried, and what's your view on this?
So this is a very good question, and let me make it a little bit more specific. Your question is whether one can actually observe those charged 2e bosons at high temperature in some way. Don't get into whether there is a quantum superfluid fluctuation or not. That's a different question. Okay. The real different question is, can we find those bound pair at high temperature? Well, Ivan Bosevich, who is also pushing a similar idea roughly at the same time when I was pushing this idea, he have been showing two things. One, in this region, in this overdose region, he convinced himself and the referee that the superfluid the density fluctuates here very seriously. Okay, and that is not a BCS behavior. That's BEC-like. That's one thing. And people ask, like you asked that question, that what about high temperature? So he worked with somebody with this sharp noise measurement, and they claimed in another paper that at high temperature, they also see in the overdose side charged 2e quanta. They didn't go that high, right, obviously. But to me, this is only suggestive, because probably Dragunov will say, well, noise measurement is very difficult. Maybe different group will have a different conclusion. I would say, no, we should wait until more experimental data are available. For me, I am not insisting this is the right picture. I'm saying that this is a very convenient picture because I managed to get most of the property already done, exactly that experiment with a trivial, intuitive answer, while many, many complicated theory cannot. So, well, I like simple thing. I like textbook. My golden dream is before I retire, all this become realized, and I will write a book, say solid-state physics 2, and start from a Bose liquid, right? Then go repeat every chapter like a textbook, except you replace the first chapter. Well, then I will be happy. Then I think I can retire. Thank you.
So on that note, on that note, I think we should move to the coffee break.
Thank you very much.
And we will continue.